What do you already know about nuclear fusion?
Oh my God. Mostly, I always confuse which one's fusion and which one's fission.
Hold on. Here's how to organize every nuclear thing you've ever heard of. Imagine that this is fission row and this is fusion row. And this is controlled and this is uncontrolled. Fission is cracking a big atom, like uranium, into smaller atoms. A little mass gets lost, energy is released. Fission uncontrolled, that's an atomic bomb. Fission controlled, that's all nuclear power that's actually usable, generating electricity right now. Fusion is smashing tiny atoms, like hydrogen or helium, together to make a larger atom. Little mass gets lost, even more energy is released. Fusion uncontrolled can be used to make another kind of bomb, the hydrogen bomb. These have been tested by several countries, but never actually used in war. And this box, controlled fusion. That's what we're talking about here.
Like, where is it? Where is it at? Because I feel like it's been on the verge of being a thing for a long time.
Yes.
Nuclear fusion. Could this provide energy which is cheap, clean, and inexhaustible?
People have been trying to do fusion and get electricity for a really long time. But now the threat of climate change and the need to find more clean energy sources is making this much more urgent. It's hard to compare energy sources while they're still being developed, but we're talking about millions of times more energy from fusion for the same amount of mass than from fossil fuels. Fission has a similar energy density, a little bit less, but fusion comes with fewer safety risks, namely nuclear proliferation. Nuclear proliferation. Namely, nuclear proliferation. Jesus Christ. Given that there are types of fusion bombs, like hydrogen bombs, why would I not be worried about nuclear proliferation with fusion?
What many people don't know is a fusion bomb is still a fission bomb. It still has uranium and plutonium in it, but it uses fusion to perhaps add some more energy. And so that's one of the primary concerns, that fusion by itself isn't a proliferation concern.
So potentially, huge amounts of energy, less risk. In order to get closer to this dream, though, we needed to move beyond smashing individual atoms together to get them to combine. We needed to do fusion at scale. Less smashing and more smooshing. And figuring out the best way to do this has been the work of thousands of people over decades. One of the images that I have in my head is when you learn about early efforts to build an airplane, you find that everyone agreed on what the airplane should do. We wanted something to help humans fly, but there are so many wonderful different images of the ways that planes were going to look.
I love the analogy of the initial work into building airplanes. So in fusion, there's a variety of concepts of ways to do this.
All of them rely on something that I have to explain first. Hold on.
I love this.
You already know that you add energy to a solid and that solid becomes a liquid, that liquid becomes a gas, and that gas becomes plasma, which many people may not be familiar with.
Ice to water to steam to other stuff that you don't see in a normal kitchen.
Yes, and plasma is all of the individual atoms themselves have broken into bits. Like there's so much energy in that system that all of the neutrons and the electrons and the protons are just like flying around in there.
This is a really good party. Everybody's like, I'm gonna leave my protons and electrons.
Single
like,
party.
yeah, no, it's like the swingers night, you can go and hang out with anyone.
Exactly. But the question is, how do you keep plasma confined and pressurize it enough for a long enough time to actually make fusion happen?
If that is atoms or like electrons kind of falling apart, like we wouldn't have any material that can contain that. Do we?
Well, there's one place that fusion's already happening a lot.
The sun.
There are three big methods that we know can confine plasma enough to make fusion happen at scale.
The one that powers the universe, and most, if not all, of the energy in the universe right now comes from fusion, is gravitational confinement. It's so large that the gravity pulls it in, pulls that plasma in, and compresses and heats that fuel to the point where it actually starts to fuse. On Earth, we don't have the ability to build very large systems that have gravitational confinement. So what we do is now a variety of using electronics and magnetic fields and other techniques to try to pull that plasma in.
I've heard about like magnetic fields and using that to keep it in place. since it can't really be in contact with other things.
That's the first method that we can actually do, magnetic confinement. This involves a machine that you might have seen pictures of. It's called a tokamak.
You heat that fusion plasma that circles around, that's well confined, until it finally gets hot enough that it starts to fuse.
However, there's another version.
I genuinely cannot guess. What would it be? What could hold it in place?
Yeah, I mean, do you have a guess? If you guess this, it would just be...
Oh, now I really want to guess it. No, I can't guess it.
Inertia.
Another big approach is called inertial confinement. And in inertial confinement, rather than trying to copy what's happening in the sun, where you're holding steady a fusion fuel until it heats and begins to fuse, now you compress it very quickly, as fast as you can, on the order of a billionth of a second.
Shooting lasers at your plasma so that it gets pushed together very quickly, and then things fuse, and then they can't hold it there for very long, and
So it's more, instead of just having a continuous plasma soup, we're having all these little plasma blinks.
It's like gravity, magneticism, and lasers.
And this is, I'm the plasma.
There are other variations on this. So the company that I interviewed the CEO of is doing a mixture of magnetic confinement and inertial confinement, magneto-inertial confinement.
So you get the confinement, you get to hold on to the fusion fuel just like the sun does, just like magnetic confinement, but you get the compression just like inertial confinement does.
This is what it looks like. This is their fusion reactor. This probably is over the course of many hours. This is the pink light that gets emitted when you do fusion.
It looks beautiful. I don't know. That's wild.
That's the plasma. What you're seeing in this progression of images is this plasma being injected from one side of the machine, compressing down, increasing in pressure and temperature. It's getting brighter, and then it starts to expand and gets a little darker.
This is a man-made star.
You're doing fusion, and you're doing it here on Earth.
That's awesome.
I love my job.
This is a really cool job.
It just feels like fusion is that thing that I'm hoping that like our grandchildren are going to be like, wait, you didn't just have electricity at the ready, like you had to burn fossil fuels? Ew, like you can just fuse atoms and then we're fine. But like, what's the catch? Because like it sounds too good to be true.
Okay. There are a couple catches. The first is that the materials that you need to do fusion aren't just your normal hydrogen and helium. They don't have the same nuclear proliferation concerns as fission materials do, but some of them are rare and hard to find. The two kinds of hydrogen that are most common used in fusion are deuterium and tritium. Tritium is rare. If we can't get enough tritium, you can do it with helium-3, which is a kind of helium.
Yeah.
Also rare. There's a controversy in the community that does fusion on like what the best materials are and which ones would scale if we wanted to do this for millions and millions of people. But the most important catch is it doesn't work yet in the way that we need it to. Like all of the fusion methods that we as humans can do take more electricity to make happen than we get out of them, which is kind of the point of an energy source. However, and this is for people that get cynical about how long we've been working on fusion.
Sounds too good to be true, right? And that's because it is.
Just another empty promise.
Decades away from effective nuclear fusion.
Just think about electricity itself. We understood that a charge could carry energy all the way back in like the late 1600s. But it wasn't until the 1800s that we figured out how to use it. That's way longer than we've been working on fusion. And plenty of people spent the time in between calling it a useless pipe dream. And the stakes of getting fusion right today couldn't be higher.
There is a real need to focus on climate change.
Fusion could be the answer to our energy needs.
Fusion has enormous potential.
I am really curious to see what the societal impact would be of having energy that would potentially be very cheap. I mean, obviously we humans are very good at hogging resources and gatekeeping in different ways, but I'm really hoping that it could be a beginning to like not having energy be so hard to come by.
And the way that it would change how you think is just totally profound. Like imagine what you could do if you didn't have to weigh the energy cost. Imagine like the total amount of human suffering that you could reduce. And then beyond that, like how you could just experiment to make people's lives better. to me, that's not just a reason to research fusion, it's a reason to invest even more in making this dream possible. It's a reason to try. Speaking of trying.
She calls me and is like, hey, how's your workshop? Can we build a fusion reactor in your workshop? And I'm like, yeah, sure. And you sent me all of these boxes. So now we have an incomplete fusion reactor in my workshop, but we will just have to leave that for another day.
But it is going to be another day. It's going to be in a couple weeks.
Oh, yeah. It's not going to be 30 years in the future that we build our own tiny little fusion reactor.
Part 2, coming really soon.